Hello, everyone. Thank you for coming to the tutorials in physical limnology for biologists and biogeochemists. The speakers today are myself, Sally MacIntyre, Bertram Bohr, and Alicia Cortez. I'm going to start by giving you some background material in physical limnology, then be followed by Bertram talking on dissolved gases and other topics, and Alicia talking about the fate of stream inflows, both in summer conditions and underneath the ice. I'll share my screen and we'll get started. So mixing dynamics, why do we care? They determine the habitat for organisms. And of course, as implicit in the name, it determines the mixing, the outcome of competition, who will be more successful, the dinoflagellates or the cryptophytes who can swim, the diatoms who are sinkers but tolerate fluctuating light, the cyanobacteria who have a lot of different mechanisms for floating and uptake of conversion of atmospheric nitrate to nitrogen to various forms of nitrogen useful for growth, but don't tolerate fluctuating light well. So anyhow, competition depends on how much organisms can be mixed around as well as their physiological attributes. Resource supply. How many nutrients come from deep in the water column? How much is an incoming stream diluted as it goes through a lake? Or does it, spread broadly or just go in and come out? The fluxes of greenhouse gases. There's many other topics that are important too, and that's just a few. So how does the field of physical limnology advance? We conduct laboratory and field experiments to identify processes. We develop and solve equations describing processes. We develop dimensionless indices and phase diagrams. And we apply these in the field, by doing experiments and interpreting our data to understand lakes as a whole and the relation of hydrodynamics to biogeochemistry and biology. Now, I want to give you an example of a phase diagram, and this is one that I suspect that many of you are already familiar with. Here, it was developed by Lewis and modified by Hutchinson, and it describes the annual cycle of mixing in lakes of many sizes and different latitudes and depths. So, for instance, in warm parts of the world where lake depths are, more than maybe 10 meters, but it's variable, the lake may only mix completely once a year, and the rest of the year it may be stratified. Many of you probably work in dimictic lakes, and these will stratify in summer, they'll mix in fall and spring, and a dimictic lake ice is going to form. So again, they stratify in the winter period. And I won't go over all these categories, I'm sure you're familiar with them, but this is an example of a phase diagram. But Hutchinson's and Lewis's schemes indicate how frequently lakes mix throughout the water column on an annual basis. And these stratification patterns set the template for growth of organisms. However, we need to know when and where mixing, that is the turbulence, occurs during the stratified periods in order to understand and quantify resource supply to organisms, the conditions conducive to hypoxia, other topics. And we want to know how patterns of mixing will change over time so we can anticipate future health and productivity of our lakes. So let's start and talk about a turbulent eddy. And this is, just a picture that came from the album of Fluid Motions, in which some milk was put into some fluid and then it was stirred, right? But what you can see is that milk has been stretched. In some places it curls up. And here you can see even more curling and even more curling. So these little curls are called turbulent eddies. And if we did the same thing in a lake, or the ocean too, of course, in a river or stream, we would see the same stretching of the fluid and the same spinning. These spinning motions are called turbulent eddies, right? And they occur in 3 dimensions. And in the upper mixed layer, they may be as deep as the mixed layer. They may be 100 meters wide, maybe they're 20 meters wide. In the thermocline, where the water column is so much more stratified, they may be 10 centimeters or 2 centimeters, right? So it varies. And the poem that goes along with this is big whirls have little whirls and so on to velocity, and lesser whirls, and the little whirls have lesser whirls and so on to viscosity. So there's a cascade from the largest eddies with the most energy down to the very smallest ones where energy is dissipated. But they're really important because they circulate phytoplankton and zooplankton. And then their size and frequency in the upper water column determines what we call the upper mixed layer, the thermocline, and the hypolimnion. But imagine if you're a zooplankton in the water, and you're here, and then you see a phytoplankton cell there, or smell it, and you're beating furiously to capture it, or you're swimming fast to get it, and that turbulent eddy just moves it away real quick, right? And you're not in the same turbulent eddy. So that's part of the challenge of living in a turbulent environment. So aquatic ecosystem studies, hydrodynamics allows us to compute fluxes. So let's look at this figure. This would be a temperature profile on a day when there's been some mixing. Here might be one where there really hasn't been much mixing. It's warmer near the surface. Then there's region with this strong discontinuity called the thermocline and the hypolimnion below. Often in a stratified lake, we think the nutrients and maybe the dissolved gases are more concentrated deeper in the water column, whereas light may be up here. This may be the euphotic zone. So that upward mixing of these nutrients is really important for nutrient supply to the phytoplankton. And we need to be able to quantify it. And the term we use to quantify it is known as a coefficient of eddy diffusivity, Kz. And the value of that, as biologists and biogeochemists, it allows us to calculate flux. And the equation, of course, is deceptively simple. Flux is equal to Kz times the gradient. And the C could be ammonia, it could be soluble reactive phosphorus. It could be the abundance of the phytoplankton themselves, but that gradient in concentration across this layer is divided by depth. The other thing, of course, we have to think about is advection. Where does this water flow? How much is it mixed in the vertical and the horizontal? And another key term that we always calculate, or like to calculate, is the flux of dissolved, usually gases, across the air-water interface. And so that's another K, often normalized to 600. And again, the equation is deceptively simple. The flux is K times the concentration of your gas in the water minus that dissolved right at the very top of the air-water interface. We don't have time in this lecture to talk about the gas transfer coefficient, but we'll spend time, especially later in the talk, going over how we calculate Kz and what are the various physical processes occurring in the water column that determine its magnitude. So as a guide to the topics in these lectures, I provide initially some background on physical limnology and provide material to provide context for Alicia's and Bertram's talks. Then I'll summarize some of what we've learned in the last several decades about processes influencing vertical exchange, that is the turbulence, which is key for resource supply to plankton and for computing metabolism. However, we need to consider horizontal exchange to address a number of coupled physical and biological and biogeochemical problems, including metabolism. We also need to address the fate of incoming streams and rivers, which Alicia will cover, dissolved gases, which Bertram will discuss. There's not time in these talks to address these topics fully. We've included movies throughout to illustrate spatial variability with a goal to develop approaches for scaling these processes. And if you have interest, we can continue beyond the tutorials at SIL. So measurements, what are some of our basic measurements? Surface meteorology, wind, meaning both wind speed and direction, humidity, long and short wave radiation, air temperature, the intensity of rain. We collect time series data, temperature, specific conductance, and oxygen at multiple depths. We measure water velocities using acoustic Doppler current profilers and sometimes acoustic Doppler velocimeters, and we measure turbulence using temperature gradient microstructure profilers or shear profilers, acoustic Doppler velocimeters, again, the ADCPs, instrumentation on gliders, and autonomous underwater vehicles. And here's an example of installing a MET station in an embayment on a lake in the Amazon floodplain. And you can, all the studies I do, I try really hard to make sure that I have a MET station on the water body or on the shore of the water body, because there's really differences over space. But here in this picture, you can see the vane for wind direction. You can see the anemometer for wind speed. In here we have air temperature and relative humidity sensors. They're shielded from direct sunlight. It's aspirated so the heat doesn't just accumulate. This station has a little PAR sensor for photosynthetically available radiation, although elsewhere we have a Kip and Zonin net radiometer, so we get full shortwave and long wave downwelling as well as upwelling. And then here you can see that we've got solar panels and a data logger. And you can tell we also fabricated our little platform. And here are examples of just some of our instruments laid out in arrays. Under the ice, we put arrays. We have them in summer conditions. We have them in the tropics. Under the ice, sometimes we get scared. One of the buoys that holds up the line is going to collapse, so we sometimes put two. And you can see our halyard line that we use and cable ties holding on the instruments. Here's a few more. Temperature measurements, mini dots for oxygen measurements. And then here, after recovering an array in winter, it's all piled up, hopefully nicely right there, the GPS to make sure we got the location right. And then we took some gas samples too. And what do these arrays look like? This is what one of our summer arrays would look like. We have a subsurface component of our array, and we have a surface component. Here's that orange float again. Here's a weight on the bottom with the amount of weight depending on how windy and how big your lake is, and the amount of buoyancy at the top. You can ask me more questions about that later. And on the array, we have temperature sensors, dissolved oxygen, specific conductivity, water pressure, so we have a chance to see if there's been a change in the depth of the water column, due to evaporation, or if it's a floodplain lake, rising or falling water. Another really important part of these arrays is that we have this surface component with a surface float. You can see it thin. And right here, we have our temperature array horizontal, not the array, the sensor. And it's very close to the surface. That allows us to calculate the sensible and latent heat exchanges accurately, because we need to know this surface temperature, also outgoing long wave radiation. And then we'll have some DO sensors and specific conductance. And we tend to put these close together because there's a lot that occurs near the surface. And depending again on the wind exposure of the lake, this upper part may be 30 or 50 centimeters, or it may be deeper, right? And so this float could be 30 or 50 centimeters, it could be a meter, it could be 2. Underneath the ice, we don't have this part. We only have the subsurface, and we know how deep the ice will form over the winter. So we try to make sure that the subsurface float is below the depth to which the ice will form. Now, I've been really happy over my career to have the SCAMP, self-contained autonomous microprofiler. It's a form of conductivity temperature depth logger. They're not made anymore, so for something similar, you may go to Rockland Scientific, but many of you might have a Hydrolab, you might have a JFE Advantech with an oxygen sensor. There's a variety of types of CTDs, but they'll measure temperature, conductivity, often fluorescence, irradiance. Here we measure photosynthetically available radiance. And the SCAMP, because it's a microstructure profiler, measures the temperature gradients in the water. And that allows us to calculate the amount of turbulence. This instrument samples at 100 hertz. The Rockland is at 540. CTDs will sample anywhere from 6 hertz to maybe 25. Anyhow, it means that you get really good resolution through the water column. And this data complements what you have with your array, because you might not be able to be in the field taking data all the time. But when you have the array out there, you may be sampling every 2 seconds or 10 seconds or every 5 minutes. And that's one picture, but these can usually give you more variables, and they also help you intercalibrate between those loggers in case your calibration isn't perfect. Okay, and again, on a surface energy budget, if we want to figure out that energy coming in that's causing the mixing of the water column, we measure the incoming and the outgoing shortwave radiation, the incoming and the outgoing long-wave radiation, and the latent and sensible heat fluxes, with latent heat flux depending on the vapor pressure gradient and wind and temperature, and the sensible heat exchange depending on that difference in temperature between the air and the water, as well as wind speed. And what do? If the solar radiation isn't too great and the loss terms exceed the incoming terms that cause heating, we'll get convective mixing. If the wind is blowing, it's going to move the water across the lake, generate eddies with mixing. And because you increase as the wind blows across, it increases the amount of water on this side, creating a head that depresses the thermocline. And I'll talk more about that later in this talk. But we measure these various variables, as I showed you before, in order to get that energy budget, to know what that energy is that's coming in to mix a lake or to tilt the thermocline. Okay, now you've already heard me say, probably epilimnion or upper mixed layer, thermocline, hypolimnion. As we've had the more advanced instrumentation, we're in a position to really see the sublayers, especially within the upper mixed layer. This whole layer here above the seasonal thermocline is the upper mixed layer. But now we know that it's subdivided into an actively mixing layer, which is, much more turbulent. A little step change will often show, which is the diurnal thermocline. And then below that is a subsurface layer, right? Then the seasonal thermocline and the hypolimnion. So if we think about the extent of turbulence, here we have turbulence is driven by wind and by heat loss. Down here, it's a little bit more intermittent, probably driven by shear, and in the thermocline and hypolimnion, same thing, intermittently turbulent. And I'll get into more of that in the later part of this set of lectures. Now, it's really amazing what we now can see with our high frequency sensors. I don't have a graph in here of what we used to get with weekly profiles. This is some of the very first data I had, probably at 10-minute intervals with some of the very first loggers that I had, and working up in Tulick Lake in actually 1999. And everywhere we have the little red stars is the depths where I had the thermistors. Here's the depth from the surface down to 15 meters. Here's time, day of year 180 to 220. So end of June until the middle of August. And with this, we can see how the lake's stratified, right? And we've got diurnal thermoclines, just as we just talked about. Actively mixing layer would be here, it'd be here. Seasonal thermocline there. We had a storm event. We could see the incoming stormwater here, and it also cooled, and then later in the summer it warmed up. So we can see a lot of details in this data, and it takes time to look at it all and digest it and really develop a picture. And that, in ongoing interactions within this overall group, we really should discuss each other's data and what we can see within that data. I'm fortunate a lot of the loggers I have are really high accuracy. They sample pretty fast. But even with loggers with, say, 0.2 degree accuracy, you can improve it if you do your own calibration. Another little thing here, which is important, notice the thermocline jumped. The explanation for that is in the later part of my talk. Now, if you measure not only temperature, but also oxygen, you can get a lot more information. So this data is from the floodplain lake in the Amazon, where I showed you that met station, although it's in an open water section of the lake. And the water depth at the time was 2 meters. Once again, the dots show you how close together we had our instruments. The upper panel is temperature, the lower one is oxygen. And we have here only 2 days of data. 333, you can guess that's about November, early December. We form a diurnal thermocline in the morning. The wind comes up, that diurnal thermocline descends. Over at night, you can see the water column becomes well mixed. In the morning, you see it heat again. And this is why we do our surface energy budgets. We can capture this and quantify it. The wind increases, diurnal thermocline descends, and it keeps on descending. And at night, once again, it mixes. The third day, the same kind of thing. Now, when we look at the oxygen, what's pretty interesting, you can see, wow, here's our numbers from 4 to 9 milligrams per liter. Got around 9 when we had that strong stratification in the morning. It's noon, bright sunlight. And then we can see, again, this mixing, just like we saw in the oxygen, in the temperature. But another thing that we can see, like here, you notice a little cold water, and here a little cold water. Well, when we look at the oxygen, okay, a lot of photosynthesis, the oxygen concentrations go up, stratified, and down here it's anoxic. The next figure I'm going to show you is a movie of the movement of the thermocline. But in fact, what's really important here is that, we had some nocturnal mixing, and the wind either relaxed or changed direction, and water from somewhere else in the basin sloshed over, and it was colder, and it was much lower oxygen concentration. So sometimes there's features that we can learn even about thermal stratification by having concurrent oxygen measurements. And of course, those of you who are interested in metabolism or primary productivity of a system, you know how essential that data is in order to calculate metabolism. Okay, and this will be the last slide in my talk, but I'm going to talk about this slide and show you a movie, and then I'm going to turn the session over to Bertram. And I'm also going to describe this figure again later. But it was done by Clifford Mortimer, and he collected data in Lake Windermere in England or Great Britain in the Northern Basin in October 1949. We have an epilimnion, we have a hypolimnion, and a very thin thermocline in between them. The wind blows, you can see the currents near the surface are greater, and then some of it downwells, and we get another flow in this direction. As that wind continues, the water from the epilimnion actually gets blown to the other end of the lake, right? And we have a really strong upwelling, right? So we have the upper mixed layers now circulating here. We've got upwelling here. We've got some mixing between the layers. And then it continues, the wind it says negligible flow here. The wind is still continued. And afterwards, we see that there's colder water here. It's upwelled, and warmer water there. It's important to recognize these processes took place in 2 dimensions. It wasn't just that we have an epilimnion and a hypolimnion, and we have a straight vertical flux. The wind blew, there's upwelling, and we have transfer from the hypolimnion upwards. Later in the talk, you'll see how we can quantify the extent of mixing as a function of this upwelling and how we predict it using dimensionless indices. But right now, I'll stop the share. It's going to come back up. I'm going to show you the movie, and then we'll come back and hear the talks by Bertram and Alicia. Now, this movie, I've always thought it was made by Ben Hodges, and he told me that Bernard Laval made it. It's from Lake Kinneret in Israel. And Lake Kinneret to the west is the Mediterranean Sea. And the winds become strong every afternoon. And as you'll see the effect of the thermocline. So upper mixed layer, thermocline, hypolimnion. This is the scale bar for wind speed. And here you can see when the winds shift. This is the scale bar for the upward movement of isotherms, these lines of constant temperature. And this is the scale bar for the magnitude of a horizontal flow. Right here is the extent of mixing, 100% to not at all. So now I'll start this movie. And the wind has come up, right? Well, first off, see how dynamic the lake is. It is not just this still little water body. When the wind comes up in the afternoon, it depresses the thermocline over on the eastern shore. There's an example of it. And that thermocline upwells to the west. And now it's downwelling again and upwelling again to the west. I'll try to capture that and stop it. But see, just as Mortimer envisioned with his cross basin temperature measurements, a lot of that warm epilimnetic water has been blown to one side. The thermocline is depressed, and we have an upwelling here on the west. You can see how water from a hypolimnion is actually squeezed, and it upwells here, and you can see how that mixing occurs. And then some of this mixed water may actually intrude into the thermocline, allowing some vertical exchange. But now, then as the wind relaxes, you can see that the thermocline kind of spreads at both ends. The mixed layer stops mixing in some places. Some of it's going to have flown back to the other sides of the lake. And once again, we can see the strong mixing. There we capture another spot in a minute. Here we go. I didn't get it, but you can see that the thermocline is just not a straight line across a lake. It's very, very dynamic with very different internal wave modes depending on the extent of wind. There's this case with the epimixed layer. It's deepened on the one side, thermocline compressed here, and upwelling occurring over to the west of the lake. Okay, I'll let the movie carry on. And okay, now I'm going to stop and now turn the rest of the show over to Bertram and Alicia. And I have one confession to make, that this part was recorded afterwards. And I listened to my own talk again this morning, and I noticed one mistake towards the very end, where I have it a little bit backwards, what the eddy diffusivities are in the warm versus the cold summer. So when you later on listen to that, go, oh, Sally flipped. She said high when it was low and low when it was high. So I hope very much that you'll enjoy the rest of these tutorials, and thank you very, very much for coming.